Hello there. Let's start talking about Atwood's machines, or in other words, pulleys. In this setup here, I just have a simple pulley with two masses labeled capital M and little m, and I want to describe the motion of the system. Bear in mind that for this example, we assume both the rope and the pulley to be massless to make our calculations much easier. We're going to start simple because we want to run down our very general kind of 5-step program here, and we're going to build up to more complicated pulley systems, over time. But if we get a solid foundation using these 5 steps with a simple example, we're going to feel really confident going forward. Not to mention, this is a physics channel, and it would practically be criminal for me not to cover the simple pulley at some point, so here we go. So, step 1, I have a system, I want to describe it with Newton's laws. Let's start by finding the degrees of freedom for our system. That's going to tell me the number of independent coordinates I need to describe my system. So to find the constraints, we start with the formula 3n minus c, where n refers to the number of bodies in our system, which in this case is 2, we just have these two masses, and c refers to the number of constraints. Alright, so let's go ahead and think about how many constraints we have here. So each of my masses, they can only move up or down as opposed to 3 dimensions. So each one has a reduction of dimensionality of 2. So we capture 4 constraints so far. And also, we have the fact that this rope is of a fixed length and it's holding the two masses together. So that is a 5th constraint. So our total number of constraints is 5. And so at the end of the day, we have 1 degree of freedom here. So we check step 1 off. So we only have 1 degree of freedom, right? But common sense, right? If I label the top of this ceiling here as, I'll call this y equals 0, right? Like common sense would tell us we use 2 coordinates, y1 to track the first mass, and a second coordinate, y2 to track the second mass, right? And you see this happen a lot. My degrees of freedom are telling me that I only need 1 independent coordinate though. So somehow, based on the constraint that this rope here is of a fixed length and is connecting these two masses together, we're somehow going to be able to relate the coordinates y1 and y2 to each other. So how do we do this? How do we relate y1 and y2 to each other? So one really nice and easy way to do this, kind of a systematic way for even more complicated pulley type problems, is to start at our ceiling. And we say, look, from our ceiling, let's write down all of the relevant distances to get to each of our masses. Okay? So from the ceiling, we go down and we start by going down, meeting at the center point of our pulley. This is going to be some fixed length. I'll go ahead and call this capital L, okay? Next, to reach our mass capital M, right, we have the next length, which is this overhang of the left rope on the pulley, okay? So this overhang, I'm going to go ahead and call little l1, okay? So let's write this down. So to get to our mass M, we have capital L plus our little l1, and what does this sum to? This sums to y1, the location of our big mass. Okay, and for the second mass, little m here, right, we go ahead and we start from the ceiling again. We have our length L, and then once we reach the center of our, pulley here, we have one more length, right, and it's the length of the overhang of the rope on the right side of the pulley, which I'll call L2, in which case we have that L, capital L, plus L2 is equal to Y2. You see that? Now, writing this out like this isn't immediately useful until you exploit our constraint. And what's our constraint tell us? It tells us that the length of this rope here is a constant. Or in other words, L1 plus L2 is always going to be constant. The amount of overhang of rope on the left side plus the amount of overhang on the right side is going to always be equal to a fixed length. If you want to add in the middle bit here, that's fine, but that's just adding another constant to the whole thing. So now, how do we rewrite these expressions capitalizing on this constraint here. Well, guess what? Look at what happens if I just add these two expressions together. I'm going to get 2L plus L1 plus L2 equals Y1 plus Y2. And look, we have our constraint that L1 plus L2 is a constant. 2L, well, again, at this length here, that's just connecting the pulley to the ceiling, is absolutely a constant. So, this is just another really big constant now. And we have this constraint. Y1 plus Y2 is always, always, always going to equal some constant C, right? And so we now see that Y1 and Y2 are interdependent on each other. Okay, so there's really, just like our degrees of freedom said, there's only really one variable that we need to track, one coordinate. If I know what Y1 is, in concept I can deduce what Y2 is immediately after. So we can go in and check off step 2. We're really going to track Y1. Alright, next, steps 3 and 4 are going to be really nice and easy. You know why? Because Y1 is a Cartesian coordinate. Whenever we have a Cartesian coordinate with Newton's laws, right, these vectorial quantities are immediately going to become really nice and easy. Because in Cartesian coordinates, you can write out Newton's second law in each direction independently of each other. So what do I mean by that? Let's start writing down the forces on each of these blocks. So on the left block here, what forces are going to be on it? Well, we're going to have mg, right, on the left block, and on the right block, little mg. And we're going to have a tension force pulling up on the left block, and we're going to have a tension force pulling up on the right block. Now, are these tensions really equal to each other? We explored this in another video. If I have a massless rope, like I have here, a massless rope has a uniform tension throughout it, and therefore the tensions on the left and on the right side of the rope are going to be equal to each other. Okay, and with this I'm going to check off step 3. But hold on a second. I wrote down the forces, but I didn't explicitly write out position vectors. I still just have my coordinates y1 and y2 here, and I've made, in other Newton's law videos, a very clear distinction between position vectors, right, and coordinates. But here's the thing, this is what's so nice about Cartesian coordinates. Let's say that I did write out Newton's second law in terms of vectors. I'll do it this one time. Okay, then I have some basis vector. I'll go ahead and call it y hat. Let's define that direction as our y hat unit direction. Alright, how do we write out Newton's second law then? I would say this is mg minus t in the y hat direction is equal to, right, m times the acceleration of this block, which would be y1 in the y hat direction, double dot this acceleration. Right, and in theory I would have to chain rule this term out. But in Cartesian coordinates, the y hat unit vector is always, 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 always going to be constant throughout time. And so any derivatives of that with respect to time are always going to equal 0. So this term here is immediately going to equal m times y1 double dot in the y hat direction. And then we end up pulling out mg minus t equals m times y1 double dot. You see that? Or in other words, I get a form for the equation of my coordinate y1 that looks exactly the same, right, as the vectorial version of Newton's second law. The general vectorial form of Newton's second law becomes the exact same form of writing out Newton's second law for my y1 coordinate. You see that? So Cartesian coordinates are extremely useful for that reason, right? And I think it goes without saying that for the little block, we're going to have the exact same equation, just little mg minus t equals little m times now its position y2 double dot. Ooh, remember though, red alert. We should only have one independent coordinate necessary to describe the system. So now we gotta reference our constraint again. Guess what happens if I take two derivatives of this guy? What am I gonna have? I'm gonna have y1 double dot plus y2 double dot is equal to derivative of a constant, 0. Or in other words, y1 double dot equals minus y2 double dot. I think it comes as no surprise that if these blocks are connected by a rope, that the acceleration, right, if the acceleration of the first block is in the positive direction, then the acceleration of the second block is going to be in the negative direction, and they're going to be the same size, right? They're connected together by the rope. But notice how generally we were able to prove this, starting from the fact just that we had this constraint that the length of our rope was constant. We were able to write all of that out mathematically and truly connect these ideas that the length of my rope being constant led to those accelerations being, equal and opposite in direction. Again, the key is to generalize the method. We're not results oriented, right? Because as these Pulley problems get harder, the constraints aren't going to give us such kind of obvious results. Okay, but now if we have this, okay, great. I'm going to go ahead and say that y2, this is equal to minus y1 double dot. And now the tension is an unknown variable in this system of equations. Let's go ahead and eliminate that guy. So I'm going to subtract the two equations from each other, and I'm going to have capital Mg minus little mg is equal to m y1 double dot plus, because minus a negative, plus little m y1 double dot, and we're going to have that y1 double dot is equal to g times m minus little m over m plus m, right? And again, we can immediately write out the acceleration of the second block, because based on our constraint, y1 double dot equals minus y2 double dot, and so y2 double dot is going to be equal to g times little m minus m over m plus m, and we are good to go, right? We've completed step 4, right? We've generated, right, equations of motion describing these two blocks from Newton's second law. Do we need to solve them? No, not really. I'm going to go ahead and check this guy off. A constant acceleration for both of the blocks is, we don't need to go through and solve anything there. We know what a constant acceleration means. Okay, I'm going to go ahead and end this video here. If you enjoyed this video, let me know in the comments and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.